Okay, last time we did a quick overview of the elements of the periodic table and just saw that the unusual shape is designed because families all have the same chemical reactivity, and so they always perform the same types of chemical reactions. So here we have the alkali metals, the alkaline earth metals. This big area here is called the transition metals. And way over here we have the halogens, the noble gases, and then we have kind of a dividing line that runs in through here, which are the metalloids. The metalloids, so a line going through here, separates your non-metals in the upper right-hand corner from your metals all the way over there. Some people have had some fun with the periodic table and have put together a periodic table books of the Bible. And so the idea is great because it's a way of organizing information. So for a Bible scholar, we have the New Testament books on the right-hand side and the Old Testament on the left-hand side. You'll see that they have organized in the periods the first 5 books written by Moses, sometimes referred to as the Pentateuch. And then on the other side they have the Gospels. Acts, the history of the church, and then you have the history of Israel in the Promised Land, in the books here. And then you go through the epistles of Paul, and then the general epistles all the way down to Revelation on the right. On the left-hand side of Revelation you have your minor prophets, your major prophets, and your wisdom literature in here. So the books of the Bible, yes, we can all get to know them, but the periodic table here is kind of trying to give you an idea of what the periodic table of elements is really all about. So let's return to Dalton's theory. In the 1800s, he came up with something that was fairly radical for his time, using an incredible amount of brain power that I believe that God gave him to understand what was actually going on. Everything that he said is true, with the exception of one thing. He didn't know about something called isotopes. And isotopes are atoms that have the same number of protons but differing number of neutrons. And so we want to find out what these subatomic particles are, and that's where we're going today, and find out how they actually make elements do what they do. So Dalton's theory raised some new questions, as theories tend to do. Dalton's theory raised the question of, if an atom makes up an element, then what are atoms made of? And so people began to explore what atoms are made up of. And our first development is a gentleman by the name of J.J. Thomson, along with some others, a guy by the name of Crookes. But he basically showed that atoms of any element can be made to emit tiny charged particles. And these charged particles eventually came to be known as electrons. And so on Vimeo, under my Vimeo, you will see a little demonstration using an old computer monitor, which was called a cathode ray tube, in order to show how those electrons are diverted. And you'll get an idea of what J.J. Thomson actually saw. So take a look at that video, pause this one if you need to, and go look at that one, so you can get a little sense of how he would have viewed what he, in his discovery of the electrons. So if we have negatively charged particles, you have to understand that an electron has a negative charge. It is part of an atom, and an atom overall is neutral. That is, it has no charge. So if there are electrons and an atom is neutral, and electrons are part of atoms, then an atom also must have some type of a positive charge. So scientists began their quest for figuring out what would an atom really look like. And they came up with what is known as the plum pudding model, which that word is not in use much anymore. So let me use the word chocolate chip cookie dough. But you'll hear me refer to plum pudding. Plum pudding is plums in pudding. So chocolate chip cookie dough is a little more familiar, and I will use that. So in the plum pudding model, they pictured the pudding bowl, something like that, and little tiny negatively charged particles made that pudding have a positive charge. So they figured the pudding itself must have some unique positive charge that would cancel out the negatively charged electrons. So if you were to imagine this as chocolate chip cookie dough, the electrons are the chocolate chips, and the dough is this positively charged mass of stuff. So the dough represents a positive mass, positively charged mass, let me say that, a positively charged mass of the atom. And they didn't know how, but they thought that it must have a positive charge because electrons have to be canceled out by neutrons. The chocolate chips would represent the electrons. So when they did that, there was a guy who comes along, a guy by the name of Rutherford, and Rutherford proposes an experiment to prove the plum pudding model true, i.e. the chocolate chip cookie dough. So he designed an alpha particle, and you don't need to know this, but for those who like to know, an alpha particle is a helium atom that has its 2 electrons taken away. So it actually has a positive 2 charge. So these alpha particles are coming out of a radioactive source, and they are shot at a very, very thin piece of gold foil. So this is gold foil, and if the plum pudding model is right, gold foil is made up of gold atoms, and all of the things that are shot at the gold foil are just going to continue straight through and hit the metal detector band only in one spot. Because after all, a chocolate chip cookie dough is going to allow something to just shoot right straight through it. Now, they expected there might be a little bit of a diversion, a little bit maybe this way, a little bit maybe this way, because after all, this is a positive charge, and positive charge with a positively charged cookie dough, shall we say, they repel each other. But on the other hand, if you also have electrons in there, electrons is an opposite charge, and it would attract. So they thought there might be a little tiny bit of diversion from perfect, but to their surprise, there were deflections that occurred at angles much, much larger than they expected, even to the point of coming back at them. And this totally surprised Rutherford, and the results of his experiment, he proved that the plum pudding model was false. It did not accurately represent what an atom was like. Rutherford discovered that the atom had a dense center that was positively charged. And sorry, that blank should not be there. A few years later, Rutherford and some co-workers also discovered that the atom contained charged neutral particles that we now call neutrons. So that dense center of positive charge were called protons, and that dense center also contained what are called neutrons. And those two particles make up the nucleus of the atom, containing P+, which I'll use to represent protons, and N0, which I'll use to represent neutrons. And If the atom were the size of a grape, the nearest electron would be about 1 mile away. So try and picture an atom is so tiny. There's the dense center of positive charge, about the size of a grape. And now go a mile away from here and your first electron would be found there. Atoms are very tiny, and the electrons are not very close to the nucleus. And that's going to cause some problems later on, because negatives should be attracted to positives, but the electrons do not collapse into the nucleus. So we need to discover why that would be true, but we'll save that for later on. So let's look at the particles that make up the atom. We have the proton. It has a mass that is much larger than an electron. So I'm going to give it the number, and this is approximate, don't hold me to this, 1836. A neutron is a little bit bigger, say 1838. An electron is like the tiny one of them all, and that's going to be 1. So the proton and neutron are 18 times as big as an electron is. That's astounding. And in fact, the size of the electron compared to its negative charge is extremely unexpected. So physicists are amazed at the fact that a proton, which has a positive charge, and we're going to assign a value of a +1, can be countered by something so small as an electron that has a -1 charge. And then we also have a neutron which is neutrally charged. It has a charge of 0. So the question comes up, if atoms are all composed of the same subatomic particles, why are they so different than each other? Well, basically, an atom contains varying numbers of protons, neutrons, and electrons. And these particles determine the very nature of it. But it is amazing. Oxygen and gold are made of the same exact materials. But one is hard and shiny. The other is invisible to our eyes, and we breathe it in. So we're really surprised that these are so different from each other, but that is the nature of matter. So, just to give you a quick idea of the importance of protons, neutrons, and electrons, protons determine the identity of an element. So when I discover the number of protons, I can say that hydrogen is an atom that only has 1 proton. Helium is an atom that has 2 protons. Oxygen is an atom that has 8 protons. And anything that has 8 protons is oxygen. Anything that has 1 proton is hydrogen. Neutrons determine the isotopes of an element. So the isotopes of an element are the same number of protons, but they have different numbers of neutrons. So when the neutrons change, we create what are called isotopes. And electrons determine the ions of an element. And notice, identity is protons, isotopes, neutrons, ions are electrons. And ultimately determine the chemical changes that it undergoes. So chemistry is really all about the electrons. We will talk a little more about isotopes and average atomic mass during our class time, and we will work on how to determine the number of protons, neutrons, and electrons when we're together. But we want to talk a little bit about the natural state of the elements before we go into those areas. and understand that most of the matter around us is not made up of pure elements. This is because pure elements tend to be reactive. And they tend to react with other materials that are around them. And there are some exceptions to that, such as what we call the noble metals, and you will recognize these names. They would be things like gold and silver. They tend to be found in nature in pure form. We also have the noble gases, which is that last column on the periodic table. And so they would include helium and neon and argon and krypton, etc. And then there are the diatomic molecules, and you'll find in our air, which is made up of nitrogen and oxygen primarily. There are some others, but those are the ones that primarily I want you to know. Actually, I should do all the diatomic molecules and show you a little trick for the periodic table. So all the diatomics are H2, N2, O2, F2, Cl2, Br2, and I2. And so to make it easy for you to find them on the periodic table, this is how they're organized. Hydrogen you will find in the upper corner here, and then you will find nitrogen, oxygen, fluorine, chlorine, whoops, sorry, that should be a capital C, bromine, and iodine. And whenever you find these in nature, they are always in pairs. So hydrogen is two atoms that are chemically connected to each other. Nitrogen would be two atoms chemically connected to each other. So by diatomic, I mean two atoms and this allows them to exist in nature. All right, so how to remember these. This is element number 1, hydrogen is. Sorry about how that highlights it. I can't fix that. And then you're going to find that these other ones are arranged like the number 7. So beginning with nitrogen and then ending at iodine, you will find that they occur looking like the number 7. So you start over here at hydrogen, that's number 1, and then you go to element number 7, which is nitrogen, and you draw the number 7 with them, and those are the 7 diatomics. So it's just an easy way to remember them. Which elements are gases in the natural state? Well, if you look at some periodic tables, they actually show them by color, but you'll find all the diatomics are gases except for bromine, which is a liquid, and also then you have iodine, which is a solid. So you've got your diatomics, accepting those two. Your noble gases as well are going to be gases. There's two elements that are liquid, bromine and then mercury. Mercury is a metal that is a liquid at room temperature, and that's a little bit unusual. Okay, so we're going to move on now to ions, and ions are going to confuse us just a little bit because somebody made a decision a long time ago that electrons would be negatively charged. And as we go through this, you'll see why the charge becomes an issue. So elements are neutral. That means each element has the same number of protons as electrons. So when protons equal electrons, your positive charges equal your negative charges, and it's neutral. Well, we've already learned that ions are elements that have a charge. So how do they get a charge? The only way they get a charge is by losing or gaining electrons. And when you lose or gain electrons, you will come out with an ion. So the same number of protons, but a different number of electrons. That pound sign is not a hashtag. That is the number of electrons. Okay, so let's take, for example, an element such as oxygen. All right? Oxygen normally has, well, only has, shall we say, 8 protons. And if it's neutral, it would also have 8 electrons. And if we look at the periodic table, what we'll see is that oxygen has a mass, so this number on the bottom is the mass number of oxygen, and we're going to round that to 16. So 16 minus 8 will give me my number of neutrons. So mass number minus protons tells me the number of neutrons. And so since the mass of oxygen is 16, the number of protons is 8, the number of neutrons is 8 as well. So oxygen forms an ion that is minus 2. That's its normal ion charge. So if this is the normal ion charge, how do I get to have a negative 2 charge? That means there must be 2 more negative charges than positive. So protons give me a plus 8 charge. And if I need to have more electrons than protons, I must have 2 more electrons. So that means I need not 8 electrons here, but 10 electrons. So what I'm doing is I'm forming an ion. I'm not saying the normal element is always a negative 2 charge. I'm saying that oxygen forms an ion, sometimes, that has a negative 2 charge. Normally, every element has no charge whatsoever. So let's go and we'll look at magnesium. We'll look at a positively charged element. And if you look at magnesium on the periodic table, let's go back and take a look at it. Magnesium can be found over here, and its normal number, its atomic number is 12. That means its number of protons. So for number of protons for magnesium, we'll put in 12. Since electrons and protons and neutrons are only whole numbers, we're going to round this 24.3 to 24. And that's going to give us our mass of magnesium. So, once again, mass 24 minus the number of protons, which is 12, will give me 12 neutrons. Once again, every element is neutral, so that would mean that there are 12 electrons. However, the common ion of magnesium is a plus 2 charge. That means I must have more positive charges than negative charges. So this means that magnesium has lost 2 electrons when it forms its ion Mg plus 2. So now oxygen forms a minus 2 charge by going from 8 electrons to 10 electrons. It gains 2 electrons. Magnesium goes from 12 electrons, loses 2 electrons, and it becomes a plus 2 charge. So the weird thing is, when you lose electrons, you go more positive. That's because electrons are negatively charged. So let's take a final look at an example. We'll take a look at bromine. Bromine has, and let's go back to our periodic table. Bromine is way over here on the periodic table. Its atomic number is 35. That will tell me my number of protons. So it has 35 protons. And let's look at its atomic mass, 79.9. Let's round that up then to 80. So 80 minus 35 is equal to 45 neutrons. And if it were neutral, it would also have 35 electrons. But its common ion is a -1. So instead of 35 electrons, it must have one more negative charge than positive charge. So it has 35 protons. That must mean 36 electrons. So it's the electrons that change, not the protons. Gaining electrons creates a negatively charged ion. That negatively charged ion is called an anion. In fact, that's how I remember it. A negative ion. So A-N-I-O-N, anion. And losing electron creates a positively charged ion. That is called a cation. We do not pronounce that cation, it is cation. So a cation has a positive charge, and anion is a negative charged. Ions are never formed by changing the number of protons. What's the only thing we can change? Only by changing the number of electrons. So, as it turns out, the group 1 metals, those are called the alkali metals. The alkali metals always form -1 ions by, +1 ions by losing an electron. Group 2 metals form +2 ions, and they do that by losing how many electrons? They've got to lose 2 electrons. Group 3 metals, aluminum and gallium, they form +3 ions by losing 3 electrons. Group 4 is a little unusual. It kind of crosses that border between metals and nonmetals, so we're going to ignore it for right now. But group 5, they form -3 ions, and they do that by gaining 3 electrons. Whoops, I left a few letters out there. Gaining 3 electrons. Group 6 forms -2 ions, and they do that by gaining 2 electrons. And finally, the halogens form -1 ions, that's called group 7, by gaining 1 electron. So the shape of the periodic table is really based on the electrons. It's the electrons that determine the chemical reactivity of any element, along with some other factors. So let's go back to our periodic table that we had way up at the beginning of our notes and look at some other information that we can put in. Alkali metals in this column, when they react, they form +1 ions. Alkaline earth metals in this column, they form +2 ions. Aluminum and gallium, these guys form +3 ions. In fact, all metals form positive ions. And then if we look at the nonmetals, These are the noble gases. They do not react. They don't form any ions. The halogens, they form a -1 ion. Oxygen and sulfur, -2. Nitrogen and phosphorus, -3. So these columns tell you that these ions form, and that's why we have the shape of the periodic table as we do.